today's lecture for Physics EP025 is about Chapter 4, Magnetism, a topic that I believe you have learned pretty much in school. So hopefully this session is going to be a bit of revision of your prior knowledge, but there are a lot more to learn about magnetism. So these are the subtopics in Chapter 4, 4.1 until 4.7. That's quite a lot. But for today's session, we are going to look at 4.1 magnetic field, 4.2 magnetic field produced by current carrying conductor, 4.3 force on a moving charged particle in a uniform magnetic field. So let's start off with the first subtopic, which is magnetic field. The learning outcomes is students should be able to define what is magnetic field, and then identify the magnetic field sources, sketch magnetic field lines for the earth, bar magnet, and current carrying conductors. So these are the magnetic field sources. Okay, so the definitions of magnetic field is a region around a magnet where a magnetic force can be experienced. If you still remember, it's quite the same with electric field. We are talking about a region, and when there is a charge goes into the region, this charge will experience force. So in this case, magnetic field, the charge will experience magnetic force. Okay, next, identify magnetic field sources. Okay, here the first source of magnetic field is the Earth, okay, a giant bar magnet. And then we have a common bar magnet. Then on the right hand side, these are three different conductors. We have straight wire, we have coil, and solenoid. So these conductors are able to produce magnetic field. And the condition is that there should be current flowing through the conductors. So the three of them are called current carrying conductors. Okay, so just to add more, the left hand side are the example of a naturally occurred magnetic field. On the right hand side is how we can produce magnetic field using conductor. Okay, we can represent magnetic field using the magnetic field lines. Quite similar with electric field lines. Okay, so the directions of the lines coming out from the North Pole going into the South Pole, as you can see in the animation over here. The lines could be straight lines or curves that do not cross each other. Each line has their own path. Okay, and in terms of the directions of the magnetic field, for the straight line it's easier to tell because if the arrow is going to the left, meaning that the directions of the magnetic field line is to the left. Okay, but for the curve, the tangent of the curve is the directions of the magnetic field. Okay, more about lines. If you see in a diagram, there are a greater number of lines, and then they are closer to each other. These two are referring to the strength of the magnetic field lines. Greater number of lines and they are closer to each other, stronger magnetic field. And if we have lines that are equally spaced and parallel to each other, this indicates a uniform magnetic field. Okay? Right, next on how to represent magnetic field, we can use crosses or dotted circles. For the crosses, they indicate that magnetic field lines enter the page perpendicularly or into the page. Magnetic field lines leave the page perpendicularly out of the page for the dotted circles. Okay, so to help you remember this, maybe you can imagine when something coming out from a hole, most of the time you will see the head first. Okay, so remember the dotted circles. And if something is going into a hole, you will see the back of the thing. So you can remember the cross. Okay, so hopefully this is going to be helpful for you. Okay, so a bit of revision. A bar magnet has two poles, as we know, north and south. If you cut the magnet in half, you get two smaller magnets. Okay, and if you cut them more, you have more smaller magnets. Okay, so you can see on single magnets, they're always gonna be two poles. There will never be only one pole. Okay, And scientists has found that when light poles facing each other and were brought together, they will repel each other. This is because of repulsive force. And for unlike poles, they will attract each other. Okay, attractive force. Right, then we go to the next learning objective to sketch magnetic field lines. So we have seen that each line has their own path. They could be straight or curved. And then we also look at crossed and dotted circles. Okay, so we are going to use them to show the Earth's magnetic field, bar magnet, and current carrying conductor. Okay, let's look at the first source, which is the Earth. Okay, as I mentioned, the Earth is like a giant bar magnet. The south magnetic pole is known as the geographical North Pole. Okay, so geographically, this is the North Pole. Okay, but this is actually the south magnetic pole. And for the geographic South Pole, this is where the North Magnetic Pole. Okay, so if we want to draw the lines are coming out from the North Magnetic Pole of the Earth going into the South Pole. Okay, so the magnetic field from the Earth is what makes compass are usable for navigation. Okay, because the needle of the compass will try to align with the north pole of the Earth's magnetic field. Okay, so next source is about bar magnets. I believe you have seen some of the pattern in school. Okay, so the lines are leaving the north pole going into the south pole. For unlike poles experiencing attractive force, this is how the pattern around them. Okay, so the north going into the south. For light poles, they will repel. As you can see, the lines over here are trying to repel each other. So there's going to be one point we call as neutral point where the magnetic force, the resultant magnetic force is zero. Okay. Next source of magnetic field, the first conductor, we are looking at straight wire. Okay. So as you can see, for a straight conductor, the magnetic field line wraps around the wire. Okay, so this is from the top view. The current is coming out of the page, so we are using dotted circles. Okay, and here we can use the right hand rule to determine the directions of current or maybe the directions of the magnetic field. Okay, as you can see here, the thumb is indicating directions of the current going up, and then the other fingers in the directions of anti-clockwise. Okay, how about if the current is going into, so we're gonna put a cross over here. Our thumb is pointing downwards, so the directions of the magnetic field is going clockwise. Okay, so we are using the right hand rules, going up anti-clockwise, going down clockwise. Next source is circular coil. Okay, so as you can see, this is a circular coil. The current coming in from one side and then going around and coming out from another side. Okay, so from the top view we can see as if the current is coming out on the left hand side and going into the page on the right hand side. Okay, so using the right hand rule, we can determine the directions of the magnetic field lines. Okay, so for the left hand side, current coming out, so directions of magnetic field is anti-clockwise. Okay, and then for the right hand side, current going into the page, so magnetic field is clockwise. So in the middle of the coil, the directions of magnetic field is the same. Okay, so we can see that here we have a stronger magnetic field. Right. Okay, the next source of magnetic field is solenoid. Okay, so this is the pattern around solenoid. You can see we have greater number of lines in the middle of the solenoid, and at the outside over here we have a bigger gap. Okay, so we can compare the strength. In the middle, the strength of magnetic field is stronger than the outer region. Okay, and here you can see we have dotted circles, meaning the current is coming out of the page. Cross current is going into the page. Okay, so this is the top view. Okay, so still about solenoid, we can determine the directions of current and also the north or the south pole. Okay, using the right hand grip rule. Still using the right hand. Okay, so you can refer to the diagram over here. So the current is coming in from the left hand side, going up, sorry, going down, up, down, up, down, up, down. Okay, so you need to use the other fingers and follow the directions of the current in the solenoid. So you can see that the directions of the north pole is on the right hand side. Okay, so the thumb is the north pole. Okay, let's say if we change the directions of the current. Okay, so current coming in from right hand side, up, down, up, down, up. Okay, so your hand should follow down, up. Okay, so now the north pole is on the left hand side. Okay, so practice using your right hand grip rule. Okay, let's do some lesson check. Magnetic field lines move from, what's the answer? Okay, so the answer is C, from north to south. Well done. Number 2, which of the following refers to uniform magnetic fields? Time's up. So the answer is B, the lines are equally spaced. Right, so we continue with 4.2, magnetic field produced by current carrying conductor. The learning objective is for you to sketch the resultant magnetic field diagram at a point. Determine the directions of B, so B is the magnetic field, by using right hand rule. Determine the magnitude of magnetic field for long straight wire at the center of circular coil, at the center of a solenoid, and at the end of solenoid. Right, so when a current flows in a conductor, wire, or coil, magnetic field will be produced. The directions of magnetic field around the wire or coil can be determined by using right hand grip rule. Okay, so for straight conductor, we can say that the thumb is the directions of current and the other fingers are the directions of magnetic field. But for the solenoid, it's going to be the thumb's going to be the north pole. Okay, and the other finger is going to be directions of current. Okay, so when we talk about magnetic field, we are talking about a region. But if you want to talk about the strength of the region, we are going to calculate the magnetic field strength. Okay, so magnetic field strength is also known as magnetic field intensity or magnetic flux density. Okay, so the symbol is P. Okay, right, so let's see for the long straight wire. Okay, so as you can see that the current is going up, so use your right hand rule. The directions of magnetic field is anti-clockwise. Okay, so you can see at point P over here, the magnetic field is going into the page. Okay, we just focus at this point. Okay, so because we have a distance of r from the point to the conductor, the magnitude of the magnetic field intensity at point P at a distance r from the wire is given by B equals to mu naught I over 2 pi r. Okay, where mu naught is the permeability of free space and r is the distance of a point from straight conductor. Okay, just use this formula for straight conductor. Okay, so what is permeability? It is the ability of free space to allow magnetic field lines to conduct through it. Okay, so consider that we have two long straight wires, okay, are placed parallel to each other and carrying same current. Okay, so when the currents are in the same direction, in this case, you can see both of the current are going down. Okay, so from the top view, we are using right hand grip rule, so the cross going into, so directions of the magnetic field is going clockwise. Okay, so for A is going clockwise, and then for B, cross and also going clockwise. Okay, so over here you can see the directions of magnetic field are opposing each other. So this one is going down, this one is going up. Okay, so we can calculate the resultant magnetic field strength at point P, BA plus BB. But in this case, because they are in opposite directions, so one's going to be negative. Okay, when the currents are in the opposite direction, one going down, another one going up. Okay, so when they comes at point P, the directions are the same. Okay, direction is the same. So to calculate the resultant magnetic field strength at point P, we are going to add BA and BB. Okay, next conductor is circular coil. So this is the pattern of magnetic field lines around the circular coil. So in the middle, we have point O. So the directions of magnetic fields are the same in the middle. Okay, so the magnitude of magnetic field intensity at point O for the center of circular coil is by using formula B equals to mu naught Ni over 2R. So this one is a bit different from the formula for straight wire. Okay, this one we have N, which is the number of coils if we have more than one loops, and then R is the radius of the circular coil. If we can go back to this one, okay, so this is mu naught I over 2 pi R. R is the distance of point from the conductor. For circular coil, we have radius. Because this is a circle, so we have radius. Okay, then we have solenoid. Okay, solenoid, we have two formula to calculate the strength of the magnetic field. Okay, first formula is for the center of the solenoid. Okay, so this is a formula mu naught Ni over L, where N over L is N, which is the number of turns per unit length. So mu naught Ni. Okay, this is at the center of solenoid. At the end of N turn solenoid, the formula is with half. So half mu naught Ni. So N is somewhere around here. Okay, lesson check. The strength of magnetic field, also known as below except. Okay, so the answer is D. Magnetic flux is a different thing. We are going to learn that in chapter 5. Okay, so magnetic field strength is the same as magnetic flux density and magnetic field intensity. Okay, lesson check 4. Two long straight wires are placed parallel to each other and carrying the same current, so directions of current is the same. Choose the correct magnetic field lines pattern around both wires when the currents are in the same directions, A or B. Okay, so use your right hand rule. So which one is the answer? The answer is A. Okay, so imagine that we have cross over here. If this is a cross, so direction is clockwise. If this is a cross, direction is also clockwise. So in the middle of the two of the conductor, directions of magnetic field opposing each other. Sebab tu kita tak ada line di sini. Okay. Lesson check 5, the magnitude of magnetic field strength at the end of solenoid. Okay, we have two formula to calculate magnetic field strength for solenoid. One is at the center and one is at the end. So which one is for end of solenoid? So the answer is D, with the half. Okay, so the last one for today's lecture is force on moving charged particle in a uniform magnetic field. The objective is to use magnetic force, determine the directions of magnetic force, describe circular motion of a charge in uniform magnetic field, and use relationship Fc equals to Fb. Okay, so the formula for magnetic force is equals to Q cross product of velocity and magnetic field. Okay, refer to the diagram and also the statement over here. A stationary electric charge in a magnetic field will not experience a magnetic force. So this is a stationary electric charge in a magnetic field. Okay, so this charge will not experience magnetic force. But if the charge is moving with a velocity in a magnetic field, then it will experience a magnetic force. Okay, so the condition for the charge to experience magnetic force is that it should has velocity. Okay, so this one is moving with a velocity, so it experiencing magnetic force. But this one does not experience magnetic force. The magnitude of the magnetic force can be calculated by using the following equation. F equals to QVB sine theta, where F is the magnetic force, B is the magnetic flux density, V velocity of a charge, Q is the magnitude of the charge, and theta is the angle between V and B. So this is a cross product. Okay, so for cross product, the maximum resultant, maximum magnitude will be during angle is 90 degree. Okay, so the angle between V and B should be 90 degree in order to get maximum magnetic force. Okay, next, how to determine the directions of magnetic force. Okay, the directions can be determined using Fleming's hand rule. Okay, so let's say we are using left hand rule. This is for positive charge. Okay, so the thumb is directions of the force, the first finger is directions of the field, and the second finger is directions of velocity. And we can also use the right hand rule, Fleming's right hand rule, but this is for negative charge. And another way to determine the directions of magnetic force is by using right hand palm rule. This one is easier. The four fingers is the directions of B, magnetic field, and the thumb is directions of the V, and coming out from the palm is the magnetic force. Okay, so this one for positive charge, this one for positive charge. Okay, so just choose which one that you think easier for you. Okay, so let's do example. Determine the directions of magnetic force. Okay, so we have B and V. Let's say we are using left hand rule because this is positive charge. So the force is where your thumb is pointing. Okay, so this one is into the page. Okay, you can also use the right hand palm rule. Okay, this one is for positive charge, right hand palm rule. So B going down, V going to the right. So coming up from your palm is the magnetic force. Okay, so the next learning objective for 4.3 is to describe circular motion of a charge in a uniform magnetic field. So you can see over here, why does the charge travel in circular motion when it enters the magnetic field? Okay, so a charged particle with a velocity moving perpendicularly into the magnetic field. Okay, so you can see the charge is going perpendicularly into the field. The particle will experience force that is perpendicular to the velocity. Okay, so the green arrow is actually the magnetic force. The magnetic force is pointing towards the center of the circular motion. Directions of the velocity changes, but the directions of F remain perpendicular to V. Okay, so the black arrow is V and the green arrow is F. So they are always 90 degrees to each other. So the magnetic force makes the particle move in circular path. Okay, so consider that we have a region of uniform magnetic field coming out of the page. So how do we know it's coming out of the page? Here we have dotted circles coming out of the page. And then this particle, positive charge going into the field perpendicularly. So how to determine the directions of the magnetic force? Okay, okay, so positive charge, use the right hand palm rule. Okay, so now we know the magnetic field is coming out of the page. So the four fingers of your hand is coming out of the page. Okay, let's say I'm pointing in my direction and V is going to the right. So coming out from the palm is directions of the force. So the charge will be moving in circular motion. Okay, so it will travel in clockwise direction. Okay, for the right hand side, we have magnetic field going into the page. Now we have positive charge travel perpendicularly into the page. So your finger should be pointing into the page, V going to the right. So coming out from your palm is the magnetic force. Okay. Okay, and then another position. So this one it will travel like this. Okay. So anti-clockwise. Right. Now we will see how to use the relationship of Fc equals to Fp. Fc is the centripetal force, if you still remember. Fp is the magnetic force. Since the path is a circle, therefore the magnetic force contributes to the centripetal force in this motion. Thus, we can equate the equation Fp equals to Fc. Fp is qvb sine theta and Fc is mv squared over r. And let's say you need to find the radius of the circular motion, you can just rearrange the formula. Okay, so you will get R equals to mv over bq, where m is the mass of the charged particle if they are using protons, so mass of proton. If they are using electrons, so mass of electron. V is the magnitude of the velocity, R is the radius of the circular path, and Q is the magnitude of the charged particle. Okay, so we are done. Lesson check 6. A negative charge with constant velocity enters a region of uniform magnetic field. What is the directions of magnetic force? Okay, so here we have a negative charge. For negative charge, we use Fleming's right hand rule. Okay, so this is F, B, and V. We are trying to find directions of F. Okay, so B going into the page, B going to the right, so B is going downwards. Okay, so the answer is C. Next, question 7. A positive charge going into the region, what is the directions of magnetic force? So for the positive charge, we use Fleming's left hand rule. Okay, so F, B, V. We are trying to find directions of F. So B going into the page, V going up, so directions of force is going to the left, leftward. The answer is A. Right, so the next one, which of the following is true? Magnetic field exerts force only on a moving charge. Magnetic field exerts force on a charged body moving parallel to directions of the field. Magnetic field exerts force only on stationary charge. All of the above. Which one is true? 4, 3, 2, and 1. So the answer is A. Okay. The condition for a charge to experience magnetic force is that it is moving with a velocity, and it should be 90 degree with the field. Okay, because cross product F equals to Q VB sine theta. The maximum magnetic force is when the angle is 90 degree. If we have B and V is parallel, so the angle is 0 degree. Sine 0 equals to 0. Okay. Okay, so that's all for today's lecture. Please fill in your attendance form. Bye bye.